In this video, we're going to review probability and statistics. This is a great warm-up question, and feel free to use this with your own students. But in this case, we have 3 doors, and we want to choose a door. Behind one of the doors is 5 points of extra credit. The other 2 doors contain extra homework. So take a moment, decide which one you would open. Now, before you open it, let's say that I'm going to take away one door that contains extra homework. So you can either keep the original door that you chose, or you can switch. So take a moment to think about what you would do before we go over the correct solution. Let's take a look at the math behind this. This is actually the Monty Hall problem, so you may or may not be familiar with this already. But let's take a look. Let's say the actual winner was the red door. So if I chose red, and first we're going to look at no switch. So if I don't switch and I chose red, then I win. And then if I chose blue and I don't switch, then I lose. And if I chose yellow and I don't switch, then I lose. So the probability of win given no switch means, when did I win? I won 1 time out of 3. Now let's talk about the probability of win with a switch. So I'm going to erase my little marks. Now let's say I chose red. Now remember, this is still the winner. So let's say I choose red, and that means I'm taking away one of the losing doors. So now I'm going to choose yellow and I lose. So I lost there. Let's say I chose blue. Well, then I'm taking away one of the losing ones. So I'm taking away yellow, which means if I switch, I'm going to get red and I win. Let's say I chose yellow. Then I take away the losing door, one of the losing doors, which of course would have to be blue, which means I would choose red and I win. So the probability that I win, given that I switched, was 2 out of 3. Now let's take a look at another very common problem, which is the birthday problem. So we looked at the Monty Hall problem, now we're going to look at the birthday problem. The birthday problem asks, what's the smallest number of people needed in a group such that the probability of any 2 of them having a birthday on the same day of the year is greater than 1/2? So that's the birthday problem, but we're going to start by looking at a revised version. So let's choose a day of the week. What's the smallest number of people needed in the group to be certain that at least 2 of them choose the same day? So if you ask a bunch of people in a group to choose a day of the week, what's the smallest number to be certain that 2 of them will choose the same day? Well, we've already studied the pigeonhole principle, and so by the pigeonhole principle, we know that the answer is 8, because if one chooses Monday and Tuesday and Wednesday and Thursday and Friday and Saturday and Sunday, that's 7 people. So the 8th person would then verify or make us be certain that 2 people would choose the same day. Let's use that same logic now on the actual birthday problem. So let's look at a probability of 0. That is, what is the smallest number of people needed in a group if it's to be impossible for any 2 of them to have a birthday on the same day? So again, we're not saying not likely, we're saying impossible. And for impossible, it would have to be 1. Because if there were 2 people, even though it's not likely they would have the same birthday, it's definitely possible. Now, what is the smallest number of people needed to be certain? Again, a probability of 1. So to be certain, and again, we're going to use, even though there are actually 366 days, we're just going to assume it's 365, so we're going to forget about the February 29th birthday. You could do it with, it makes it more complicated because you're not equally likely to have that birthday, so we're just going to stick with 365. So for 365, that would be how many days in a year, which means we would need 366 by the pigeonhole principle to be certain. So now the question is, what's this number? So before we actually talk about that, I want you to make an estimate. So think about a number anywhere from 1 to 366. So you might choose something close to halfway through. You might choose like 175. You might say, no, that's too many. Let's choose 50. You might say, no, that wasn't enough. You might choose 200. So choose what number you think, and then we're going to talk about the math involved. So go ahead and make your estimate now, and then we will go through the math and we will figure out the solution to this problem together. So before we go through the math, let's go back to the weeks example because the math is going to be the same. So for 2 people, what's the probability that there's no match with 2 people? So if you think about 2 people, we know, and this is the probability, no match with 2. The first person can choose any day of the week he or she wants. The second person can choose any day except for whatever day this guy or girl chose. So essentially, my answer is 6/7. So that's the probability for no match. Now remember, we're looking for at least one match. We want to talk about the math involved in that. So if you remember back to when you studied probability, we know at least one is the complement of none, because I could go through and figure out all of the different ways, and obviously for 2 people it's very simple, but all of the different ways where you could get at least one match. But if I said I have 1,000 people, going through all of the ways at least one match would happen, 1 match, 2 matches, 3 matches, 4 matches, etc., that would be very cumbersome. So we're always going to use the complement. So here, at least one match is going to be 1 minus 6/7. So it's going to be 1 minus whatever I get here. So now let's look at 3 people. What is the probability for no match? So again, the first person, 7 choices, the second person, 6 choices, the third person, 5 choices. And then at least one would be 1 minus that solution, or in this case about 38%. For n people, so now we're looking at the bigger picture. If I just wanted to choose n, now what? Well, again, we can see that we have a pattern here, 7 over 7, 7 minus 1, 7 minus 2, 7 minus 3, 7 minus 4, etc. So essentially we're saying 7 minus n minus 1, because this was the first guy, this was the second guy, this was the third guy, etc. And then that's the nth guy, or girl, not to be gender specific. So now let's look a little bit further into the real birthday problem. So the real birthday problem, we have 365 choices, but you'll notice this is the same math. 365 over 365 times 364 over 365. We take 1 minus that for the solution, and we continue that for 3 people, and then of course for n people as well. We have the same pattern. Now what I don't like is this is a little bit cumbersome. So what I want to do is I want to write that a little bit nicer. So let's take a look at how we might do that and then find the solution. So this is exactly what I had on my last screen, but again, it's cumbersome. What I wanted to do was write it a little bit nicer. So I want you to note what I did here. And again, we're looking at permutations because we don't care about the order. So what I've done here is I've replaced all of this in the numerator with this, because essentially this was a permutation of 365 choose n, and so 365 factorial over 365 minus n factorial is how we would write that. So I just replaced it with that to make it nicer. And then of course this is 365 n times in my denominator. So here's my equation, and what I would like you to do before we go through the solution is pause this video and go ahead and try your estimate. So a few slides ago I asked you to make an estimate, and really you're just going to plug that into your calculator and replace n with your estimate and see what you get. Now remember, it's 1 minus that, and our goal is to get to 0.5. So take a moment and do that, and then we'll talk about how I solved it. So hopefully you plugged in your value, and maybe you got a very high number, maybe you got a very small number. What we can do is we can let technology graph it for us, because I didn't want to have to try to solve for n. That would have been very difficult. And really, it's basically just a try a number and see if it works. So whatever your number was, if it was too high or too low, then you could adjust accordingly. So I went ahead and graphed this, and you can see that this point here was almost 23, and then this was 0.5. So I plugged in this equation exactly as it was, and so our solution is about 23. Now you might be thinking that seems really low, but essentially this is an exponential equation. So we can see here how quickly it grows, and then it continues on at 1 forever once we get to a certain point. So our solution is 23, and again I took the easy way out by letting technology graph it for me. All right, let's switch gears again to another probability question. Oliver is training to be a drug-sniffing dog in that he is to bark when he smells drugs. Experiments have shown that Oliver will correctly bark at drugs 97% of the time and mistakenly bark when there are no drugs 1% of the time. So again, here we're looking at 97% versus 3% that he misses, and then 1% mistakenly, but 99% he is correct when there are no drugs. If it is found that 1 out of 10,000 packages contains drugs, how many times will Oliver bark, on average, for every 1 million packages he checks? Should Oliver continue to be a drug dog? So then I'm asking you to find the probability that, given there are drugs, that he barks, to determine this. So there's a lot going on in this question on purpose. If you've taken MA215 recently, this type of question might look familiar to you. If you haven't, that's okay too. I want you to press pause and try this question on your own. When you're ready, press play, and we're going to go through it together. So the best way to go about this is to make a probability tree. And essentially what I did is I looked at the fact that there were two different variables going on. There's, are there drugs or not? And then does he bark or not? And the reason I chose to make a tree is because these values were different than these values, which means if there were drugs, his percentages were different than if there were not drugs. So I made my tree diagram, and remember, these values are the most important values. And where did they come from? This was 0.0001 times 0.97. And then I'm just multiplying probabilities. It's the product rule. Again, keep in mind that these two values add to 1, these two values add to 1, these two values add to 1, these four values add to 1. Now, my expected value for whether he barks or not is, this is 0 times that he barks, so that's the no bark, this, and essentially I just added those together. That's where that value came from. And then the probability that he does bark is this value, which I added together. Then to find the next value, we're going to take the expected number of times that he barks. So if he barks 0 times, I take that times 0.989904 and get an expected value of 0. If he barks 1 time, I take that times the probability and get this value. So my expected value is the sum of those two, which is essentially 0.00100096. Now the question originally said out of 1 million packages, so notice I'm just going to take the expected number of times that Oliver barks for one package and multiply it by 1 million, because this is what I found here is the expected number of times per one package. So in 1 million packages, he's going to bark 10,096 times. And now I'm going to find the probability of drugs given that he barks. So we know he barks 10,096 times. And I want to find the probability that he barks. Well, he's barking, again, by taking drugs and bark, which is right here, drugs and bark, over, and again, whenever we have a conditional probability, it's always just I'm sorry, the two of these together, the intersection of those two sets, over every time he barks. So he barks here and he barks here. So I had to add those two together. So he barks correctly less than 1% of the time, and that's not great. So even though it seemed like his numbers were pretty good, he makes a lot of mistakes, so he should stick with being an emotional support dog and not a drug dog. Okay, we're going to do a little card trick, and it's going to be a little bit more difficult because I'm not here in the room with you. So we're just going to go with it anyway and do our best. I'm going to ask you to choose any number between 1 and 10 and keep it to yourself. That's your key card number. What I'm going to do is I'm going to flip the cards over slowly, and obviously since this is a video, I'm just going to put the cards up on the screen, and I've put them out there in random order. When your card's key position shows up, that will tell you how many more cards to go through to get to your next key card, which continues until you run out of cards. The last key card is your final card. If you get a royal card, Jack, Queen, or King, your key value is 5. For example, let's say my original number was 3, then my third card, say this is the first card, second card, third card, I would count 1, 2, 3, and that gives me 9, which means now I would count 9 more cards to get to my next key card. So essentially I'm just going to keep making new key cards. So number between 1 and 10, keep it to yourself, and then you can either go through it with me, or you can either pause when we get to the next screen and go through it without me, or let me do my example first, and then you can do yours. So let's take a look. My key card is 7. So 1, 2, 3, 4, 5, 6, 7 is this card. That tells me to go 7 more cards. 1, 2, 3, 4, 5, 6, 7. That tells me to go 2 cards. 1, 2. That tells me to go 10 cards. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then 6. 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5, 6, 7, 8. And then 1, 2, 3, 4, 5. Remember, that's 5 cards. And then 1, 2, 3, 4, 5. That's 1 card. And then 1. That's my last card. So my key card is 10 at the end, or sorry, 5 at the end. All right, let's take a look. That was for 7. Now let's try it for 3. So if my key card was 3, 1, 2, 3, that tells me to go 8. 1, 2, 3, 4, 5, 6, 7, 8, that tells me to go 6. 1, 2, 3, 4, 5, 6, that tells me to go 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, that's 5. 1, 2, 3, 4, 5, and 1. And notice I ended up at the exact same value. And I'm not going to go through any more numbers, but I'm going to assume that whatever number you chose, that hopefully you ended up at the same value that I did, which was a key card of 5 or a jack. Let's take a look at how this might work. Again, at the original question, I asked you to pick a card from 1 to 10, so the probability that 2 people pick the same key card is 1/10 or 0.1. What's the expected value? Again, of just that first card, which is adding up 1 through 10, dividing them by 10, because it's just basically the average. So I could have picked any number from 1 to 10, divide that by 10, I get 5.5. Now, if we count the royal cards as 5, the average length of each additional step is 1 through 10 plus Jack, Queen, King, the 3 5s, divided by 13 because there's 13 choices, so 5.38. So essentially what we're saying is the density of the key card can be expected to be 1 divided by 5.38 or 1.186. So if the magician chooses an average of 8 key cards after the victim's first, then each of those cards has a 0.186 chance of being one of the victim's key cards and a 0.814 chance of missing. The probability of the magician not hitting one of the victim's key cards on the first try or the later choices, again, because there's so many times that we're going through this, is 0.174. So the magician will win around 0.826% of the time, so 82.6% of the time. So again, I didn't go through every card or every value from 1 to 10, but it's quite possible that each time everybody got a jack, but it's also possible 0.174 or 17.4% of the time that I'm wrong, and they're not going to end up at the same value. For your homework, what I want you to do is these 5 questions, but I don't want you to submit because we're going to talk in our next class about a homework quiz. So do each question to the best of your ability, and then we'll talk about a homework quiz next time.